Donc, bonjour tout le monde, bienvenue de retour. Donc, on va passer avec la prochaine conférence. Je suis heureuse de vous présenter Laurence Perreault Levasseur. Laurence Perreault Levasseur est une astrophysicienne et professeure adjointe à l'Université de Montréal. Donc, elle mène un groupe de recherche qui se concentre sur l'intelligence artificielle dans la cosmologie. Et la grande question qu'on va répondre aujourd'hui, c'est... Désolée, je suis à la mauvaise page. L'intelligence artificielle est-elle appelée à transformer notre compréhension de l'univers? Alors, je vous demanderai d'accueillir Madame Laurence Perreault Levasseur.
Thank you so much for your commitment in coming to see my talk, given that there's the astronauts that are talking right now. In the spirit of bilingualism, I'm going to be giving the talk in English, even though my slides are in French. So the question that I wanted to discuss today is artificial intelligence and machine learning going to change the way that we see the universe? And the way that I wanted to sort of go about answering this question is sort of starting by presenting what is the current model that we use to describe the universe and its main component, which are inflation, dark matter, and dark energy, and then how machine learning is now changing the way that we do science to understand better those components. So let's get right into it. So cosmology is basically the study of the history of the evolution of the universe. So here I'm showing the timeline of the universe as we currently understand it. And one of the things that are really fascinating about our universe is that we think that everything that we see around us today, from galaxies to stars to you and I, came from quantum fluctuations at the very, very beginning of the universe on extremely small scales. And so what we think happened is that at the Big Bang, which is here on the slide, those tiny quantum fluctuations were expanded exponentially fast through a period that we call inflation, to cosmological scales here. And then after this period of inflation, the universe was very hot and dense, and then slowly cooled down until all of a sudden, the light from the cosmic microwave background was emitted. So this is what is shown here. And then this light sort of traveled basically unaffected throughout the evolution of the universe as the first stars were forming and as the first galaxies were forming all the way to us today, where we can observe it. So here I'm showing this light as seen by Penzias and Wilson in the 60s. So this is remarkably uninteresting. And it took 30 years of extremely hard work to be able to finally observe tiny fluctuation inside of the temperature of that light by the COBE satellite in the 90s. And then there was WMAP, and then finally Planck over the last decade. So Planck was a satellite that also observed the CMB. And so even though it's really amazing to see the structure of those small fluctuations in temperature in this light that comes to us from almost the Big Bang, it's really important to remember how remarkably homogeneous the temperature of this light is. So what that means is that if I look at the sky in this direction, and in that direction, the light that comes to us from the Big Bang is basically exactly the same temperature. And that is truly remarkable, because there's sort of no real explanation as to why this should be the case if we look at the standard Big Bang scenario. So that is the model that we had before inflation. So more specifically, there was no explanation. So the only region of the sky that would have had time to become homogeneous since the Big Bang up to the emission of this light would have been something about 1 degree in size, something about that size. And so there was no real reason for why the whole sky should be exactly the same temperature. So that's what we call the horizon problem. There's another problem with the standard Big Bang scenario, which is called the flatness problem. So this says that if we look at the solution to Einstein's equation, a flat universe is an unstable solution. So there would be no real explanation as to why the universe is as flat as we observe it today. So that's what the flatness problem is. And so Inflation is the theory that was proposed to solve the horizon and the flatness problem. So what is inflation? It's a period of time in the very early universe where the expansion of space was exponentially fast. So that means that all the physical distances between objects was growing exponentially quickly because the fabric of space-time itself was growing exponentially fast. And so how does this solve the horizon problem? Well, it's a little bit as if we think of the universe as a loaf of bread. So all of space is like a loaf of bread. Even though the bread starts, the dough is initially very ununiform, we can have a lot of small bubbles inside the dough. As the bread grows and grows and grows and inflates, eventually we end up seeing only a tiny patch of the dough that started out homogeneous to begin with. So horizon problem checked. And then how does it solve the flatness problem? A little bit like in the analogy of if you think of the universe as a balloon. So when a balloon is uninflated, it can have a lot of curvature, but as we blow it up and it inflates more and more and more, if we sit on the surface of the balloon, locally it's going to look like the universe is flatter and flatter. So flatness problem checked. So one of the other things that's really amazing about inflation is that not only does it solve those two problems, but if we go back to this map of the CMB, it makes very specific prediction for what the structure of all those little fluctuations in temperature should be. And if we compare those predictions to observations, there is such a good level of agreement that it's considered one of the biggest successes of modern cosmology. So that's really fascinating. And another thing that's also really fascinating about this map is that if we look at the shape of those little fluctuations very carefully, they seem to point towards the existence of a new form of matter that does not interact with light and that we call dark matter. So in fact, if it was not for dark matter, the shape of those fluctuations would actually look very different. And so we can use that to infer that there should be about 5 times more dark matter than regular matter in the universe. So these sort of cover the 2 main components of our standard model of cosmology. Oh, no, sorry. So I'm not there yet. So now that we know how mass is distributed in the universe, and in particular dark matter, we can go and try to understand how the stars and the galaxies and all the structure that we see in the universe today form. So the way that we do this is through computer simulations. So we distribute dark matter in a way that's very similar to the way we see it to be distributed thanks to the CMB. And then we just let gravity do its job. So here I'm showing the result of one such simulation that's called the Millennium Simulation. And as you could see, at the beginning, everything was very homogeneous. But then as time passes and billions of years pass, we start to form those clumps of dark matter. So those nuggets are called halos of dark matter. And here I'm showing another example of a fly-through the same simulation. And so the way that we understand how galaxies form, we think that galaxies form inside those nuggets of dark matter, inside those dark matter halos. And so smaller halos would form smaller galaxies, and bigger halos would form bigger galaxies. And what is fascinating is that with this model, we can go out in the universe and compare the result of the predictions of our simulations with observations of real galaxies. And when we do that, we realize that the two are in almost perfect agreement on a very large range of scales. So this is really amazing. So we now have the 2 main components of our standard model of cosmology, inflation and dark matter. So if we go back to the timeline of the evolution of the universe, there is a new observation, relatively new observation that was made about our universe in the latest stage of its evolution that points toward the fact that we are currently entering a new phase of accelerated expansion. And the cause for that accelerated expansion is what we call dark energy. And so dark energy was first measured using the explosion of a specific kind of stars. But since then, it was measured using various probes, and we have measured its property relatively well. So if we put all those ingredients together, we end up with the inflationary lambda CDM model, which is our standard model of cosmology. So inflationary, because it starts in an initial period of inflation, and then lambda CDM stands for its current content. So lambda, it stands for 70%, about 70% of dark matter, and CDM is cold dark matter, so it stands for about 30%, 25%, sorry, 70% dark energy, 25% dark matter, and then the remaining 5% is the regular matter that you and I are made of. And so everything that I've talked about so far was sort of trying to convince you that this model is really amazing at describing all the observations that we have of our universe. And so at this point, we could ask, are we done with cosmology? And the answer is, well, obviously not, because otherwise I wouldn't be giving this talk. So the point is that we don't know anything about the true nature of any of those main components of our standard model of cosmology. So for inflation, we don't know anything about the particle that is causing inflation to happen. But dark matter, apart from the fact that it gravitates, we have not measured any of its properties. And then about dark energy, we have no idea about what it is, like not even the slightest idea. And so in the coming decade, there is a new generation of telescopes that are going to be coming online that are going to attempt to answer all of these questions. So basically trying to unveil the nature of all the three main components of our standard model of cosmology. And the main theme underlying all those new experiments is really big data, because those new telescopes are really going to generate an unprecedented amount of data for astrophysics. And so this is where machine learning has a huge potential to help us analyze this data and make important new discoveries about the nature of our universe. So for the rest of the talk, I'm going to be going through all those components one by one, and and explain a little bit more in details how machine learning is helping us to understand better the nature of each one of these components. Inflation, so as I described before, is defined as a period of a time in the very early universe where the expansion of space was exponential. And so what that means, is, as I said before, is that the physical distances between objects was growing, was expanding with time, and because the fabric of space-time was expanding with time, and that expansion was exponential. So I have purposefully not told you how to make that happen, what kind of particle you need to make that happen, because actually theorists have a lot of imagination, and we have a lot of different models of inflation. So here I've shown only a very small fraction of the possible models that we have for inflation. So one of the main goals of of very early universe cosmology is to use observations to put constraints on those different models, and then sort of unveil which one of these classes of model is correct. And then in this way, we hope to learn more about what possible extensions to our understanding of physics is correct, so learn new physics from this. And so there's a new generation of telescopes that are going to be coming online in the next decade that are going to be measuring the prediction of those different models with unprecedented accuracy. And so nothing that I've talked about so far really had anything to do with machine learning per se, but it's actually related, because one of the probes that we want to be using to constrain those different models of inflation is the B mode of polarization. So that light that I talked about that comes from the Big Bang is actually partly polarized, and different models of inflation have different predictions for what that polarization should look like. And so by measuring it, we can constrain which one of those models is correct. But this measurement is extremely difficult to make, because there's a lot of things that are in the way between us and the Big Bang. And in particular, there's our own galaxy. And our own galaxy has a lot of polarized light that is coming from it. And so it's a huge challenge to be able to subtract all of that polarized light from this signal that we want to observe that comes from the Big Bang. And so there's two places where machine learning is really going to help us. So what we've shown in the recent years is that we can use machine learning to produce better models of what the emission coming from the galaxy should look like. So having a better model for the emission from the galaxy is going to help us subtract it better, and so we're going to have a better map of the true signal that comes from the CMB. And then the second way it can help us is by helping us extract more information from the data that comes from the telescope. So really make the most out of the investment that we made by building those telescopes, by extracting as much information from the data as possible. So this is a little bit related to some things that I'm going to talk about in the last part of my talk. So I'm going to leave it here and move on to the next part of the main component of the universe, of our cosmological model of the universe, which is dark matter. Before getting started about all the exciting research that we're doing here to learn more about the nature of dark matter, I'm first going to start about telling you how we know about dark matter, what we think it is, and what we hope to learn about it. So dark matter can be seen in many places in the universe, but one of the places where it was seen is in clusters of galaxies. So what clusters are, they are groups of hundreds to thousands of galaxies that orbit each other. And by looking at how fast they orbit, we can actually measure how much mass there should be in the cluster, because gravity is the glue that's holding the cluster together and preventing those galaxies from flying apart. So that's exactly what Fred Zwicky did in the 30s. And to his amazement, he realized that there needed to be about 5 times more mass in the cluster than what he could see through his telescope. So there seemed to be an invisible form of matter that was filling the cluster and holding it together. So now we can go inside individual galaxies and perform a similar measurement by looking at how fast stars, individual stars, are orbiting around the center of galaxies. So if we do that, we realize that once again, there needs to be about 5 times more mass inside galaxies than what we can see through our telescopes. So there seems to be this mysterious form of invisible matter that's filling the universe everywhere, inside galaxies, inside clusters, and everywhere else. And this matter is completely invisible. The only way that we know about its existence is through its gravitational influence. And so the million-dollar question is, what is this new matter? And our best guess for this is that it should be a new particle, like an electron or a proton, but that does not interact with light, and that's what makes it invisible or like completely transparent. And then from there, now the race is on to go in the lab and try to build an experiment to measure the new properties of this particle and what extension to the standard model of particle physics we need to come up with to explain the existence of such a particle. So there's a lot of experiments like this, but for example, on board the International Space Station or deep inside abandoned mines down on the Earth. But after about 30 years, or like many decades of looking, actually, we haven't found this particle yet. And so us astrophysicists, what we hope to do is to look in the sky and try to measure new properties of dark matter, of this particle of dark matter, to learn more about its nature. So what we want to do is map out how it is distributed in the universe, and in particular inside galaxies. So it's a little bit like looking at clouds. So when we look at clouds, some are very smooth, some appear very clumpy, and by measuring their clumpiness, we can infer something about their temperature. So we want to do exactly the same thing with dark matter. We want to map out how clumpy it is inside galaxies, and then with that, we're going to be able to infer what is its temperature and other of its particle properties. So one of the best ways that we can do this is with something called strong gravitational lensing. So strong gravitational lensing is a natural phenomenon, and I'm showing an example here. So we have 2 galaxies in the image. Everything's a galaxy, but there's 2 main galaxies. So this one here in the center, orange, and there's another galaxy in blue whose image is really getting distorted by the gravity of the orange galaxy. So how does this happen? So this happens a little bit in this way. So let's say that here we're on the Earth, and there's 2 galaxies, one right behind the other. As the light of the background galaxy passes near the foreground galaxy, it gets bent, and so it comes to us from these different angles. And so what happens is that here on the Earth, we see basically multiple images of the same background galaxy. So it's a little bit like looking at a fish from the corner of a fish tank. You can see multiple images of the same background fish. So here I have Mr. Mango demonstrating this effect. So as you can see 2 images of the same fish. So this is really similar to an actual image of a strong lens that we can see in the sky. So we have 2 images of the same background galaxy because of the deflection of its light rays by the foreground galaxy in orange. And so here I'm showing more examples of strong lenses. So one common feature that we see here is that it's very typical for strong lensing to produce arcs of the background galaxy. And the reason for that is the geometry of the lens. So I've actually prepared a little video to show you how you can reproduce that effect at home with a wine glass and a candle. So what you need to do this is a wine glass and a candle, and it also helps if you have a bit of wine and maybe also a buddy to drink with so that you don't end up drinking alone. So if you dim the lights to make the atmosphere more romantic and you pick up your wine glass, you can see through the foot of the wine glass that the image of the flame of the candle starts to wrap around the foot of the wine glass and produces an image that's really similar to images of strong gravitational lenses that we see in the sky. And so what we want to do is basically use this phenomena to map out how the matter is distributed in the lensing galaxy, so in the foot of the wine glass. So it's a little bit like what I'm showing here. So we want to discover if the matter inside the foot of the wine glass is very clumpy or if it's very smooth. So it's a little bit as if there were droplets of water on the foot of the wine glass. They will cause an additional level of distortion, and that's what allows us to spot them very easily. So that's what we want to do. So right now, we know very few strong gravitational lenses because it's a very rare phenomenon. 2 galaxies need to be almost perfectly aligned with each other. But in the coming decade, with new surveys like LSST and Euclid and WFIRST, we're expecting to discover about 200,000 new strong gravitational lenses. So that's super exciting for this science. But the question is, how are we going to analyze 170,000 new strong lenses? So if we assume that it takes about 3 days to finish the analysis of a single strong lens, it would take about 1,400 years of a person's time to finish the analysis of all of the LSST lenses. And so clearly we need new analysis methods. And that's where artificial intelligence and machine learning comes to the rescue. So the kind of models that we use for this specific application are a type of machine learning that's called neural networks, and more specifically convolutional neural networks. So those are really widely used in a lot of different science applications. Like, for example, in self-driving cars, these are the kinds of networks that tell you what is around the car, or in Facebook or iPhoto, it's the kind of networks that tell you who is in your photos. So the kind of application that we want to do is a little bit different. So instead of showing it the image of a dog and asking the network, is this a dog or not, we wanted the network to predict a property of the dog, like what's the age of the dog or what's his mass. So Spark is a very old dog, and he's also pretty chubby. So more specifically for us, we wanted to show the network images of strong gravitational lenses and then have the network predict properties of the mass distribution, like the mass of the lensing galaxy, its position, so things like that. So the same way that babies learn when we show them examples, machine learning models, they learn when we show them a lot of examples. So we had to show the neural network a lot of different examples of strong lenses, and then once it was trained, we could test its performances on new examples and also new images from the Hubble Space Telescope. And this is what we got. So here what I'm showing is the prediction of the network on the y-axis and the ground truth on the x-axis. So if the network was perfect, this would be a perfect diagonal line. So we see that we have a pretty good way of estimating the parameters of strong gravitational lenses. But the main point here is that this is 10 million times faster than with traditional methods. And so what it means is that instead of taking 1,400 years to finish the analysis of all of the LSST lenses, it would take half an hour on a laptop. So this could potentially really be a game changer. So the last sort of technical point that we have to address is that if we are going to use this on real data, we need to have a way of measuring the error that's caused by using the gravitational those machine learning models. So in the recent years, me and my group and a lot of my colleagues, we've spent a lot of efforts developing ways to estimate the uncertainties of machine learning models when we analyze data. And so the good news is that it turns out that it is absolutely possible to use machine learning models in a very well-defined statistical frameworks and have trust in their results. And so now it's been shown that it is possible to use machine learning for tasks where we want to use those deep learning models with their uncertainties in places where we need a lot of accuracy in order to be able to extract information, for example, about the properties of dark matter from images of strong lenses. And so this is a paper that came out a couple months ago, so very recent. And so it shows that we can actually combine the measurement in different lenses and have very good constraints on the temperature of dark matter. So this was done on simulations. And so now the race is on to show that we can actually do the same thing on real data and prove that we're actually ready to face the flood of data that's going to be coming with LSST. And so with about 200,000 new strong lenses that are going to be coming in the next decade, we really are going to be in a very good position to put tight constraints on the distribution of matter inside galaxies. And so we're really going to be poised to make very important discoveries about the nature of dark matter. So this covers the second component of the lambda CDM model. So let me now move on to the last component of the main model of cosmology. So I have no idea how I'm doing mid-time here, because I have no idea what time I started. I have 2 minutes? OK, so let me just move on very quickly through dark energy. So dark energy is basically, so how do we know of its presence? So if we throw an apple up in the air on the Earth, we expect the apple to come back down. But what happens with dark energy is that we see that the apple keeps on going up. Not only that, but it keeps on accelerating upwards. So it's very counterintuitive. So, and the cause for that is dark energy. So dark energy is also very weird because it doesn't dilute with the expansion of space. So when we have regular matter and space is expanding, it's going to dilute because there's more space, so its density is going to go down. But dark energy doesn't do that. Dark energy's density remains constant. So that means that the more expansion of space there is, the more dark energy there is. So that's contrary to any other kind of matter that we know. So in the coming decade, new experiments are going to be probing the latest stage of the expansion of the universe to try to learn more about what is this new matter. What is this new energy? Does it come from a new particle, or do we have to modify our theory of physics to explain it? So I'm going to skip this part and the way that we're going to be measuring it, but just as a last point, there's sort of like two main problems that we are going to have to solve to be able to measure more of the properties of dark energy. So the first one is, how are we going to connect our observations to the parameters that we want to measure? And the reason why this is a huge challenge is that in order to do that, we need to have good ways of producing simulations. So here, I don't know if it's going to play, but I'm showing us an example of a cosmological simulation that's called the Illustris simulation, but those simulations are extremely expensive to run. So they take hundreds of millions of CPU hours, and so we have extremely few of those. So having enough simulations in order to be able to analyze the data is a huge challenge. But what we've shown recently is that we can actually use machine learning method to accelerate those simulations by millions of times, and so be in a position where we can run enough of those simulations to analyze the coming data. Another point that's going to be a huge challenge is how to clean our data from foreground contamination, so things like emissions coming from our own galaxy. So if we look at an image of the sky and in the frequency of the emission of neutral hydrogen, which is a probe that we want to use to be able to measure properties of dark energy, we see that the only thing we see is basically the galaxy. So we have to clean this map one component at a time in order to manage to extract the signal of interest. And the main challenge here is that the signal that we want to see is 10 to the 5 times smaller than the size of the foreground. So this is really a huge challenge. So here at University of Montreal, in the last year, we have created a new collaboration, a new science collaboration with other partners around the world, where we are going to be developing new machine learning models that are really tailored for this, and we're going to be measuring new properties of the universe and dark energy thanks to this. So I just want to finish by showing this slide once again and emphasizing once again the amazing power of machine learning methods to discover new things about all the components of our universe. Thank you.
Donc, on remercie encore une fois Laurence Perreault Levasseur pour sa conférence. Une autre main d'applaudissements, s'il vous plaît. Donc, vu l'alarme de feu puis le fait qu'on veut faire des synthèses, on va prendre une seule question. Donc, dans le public, est-ce qu'il y a une question pour Laurence?
Maybe it's very naive, but I was wondering how much bias in the images do you think it could be because they will be coming from only one telescope? Do you think it will be better if there were like more telescopes to compare, or that gives more consistency for the algorithms to run on the images?
So there's actually multiple telescopes. It's not just one telescope. There's a very, very large number of telescopes. And those telescopes, usually they observe the data in multiple bands. So it's a little bit like CCD cameras here that we have. They observe images in RGB channels, so you can make color images. So we typically have a large number of those channels, so like 7 or 8 channels. So we actually have a large number of independent images, even with a given telescope. But we also have a very large number of different telescopes. So I mentioned LSSC, so this is the way that we're going to be discovering a lot of those lenses. So there's also Euclid that's going to be it's going to be a satellite, so it's going to observe the whole sky. So there's a lot of lenses we're going to be seeing with both of those, and then we're going to be doing follow-ups with other telescopes, like the ELT and other upcoming telescopes, or with ALMA, which is another telescope that's in the southern hemisphere, that we can do follow-ups of those data. So yes, we have access to multiple data sets, and then doing, like, how do we tailor to our algorithms to a specific telescope is also like a whole question.
Yeah, I was wondering, yeah, like if you got into that, and if that problem is like a big problem. And I come from health science, where, you know, like the source of the data is like a big issue there. So I was wondering if it was the same thing.
Yes, so this is actually, so one of the big advantages that we have compared to health is that we have really good simulation pipelines. So we can simulate a lot of our data, and we understand the noise statistics very well. So for us, it is a very important challenge, but it's not the biggest challenge to be able to produce very realistic simulations of a specific noise properties, for example. Thanks. But it's a really good question.
Donc, merci beaucoup pour la question. On va passer à la synthèse maintenant. Donc, ce que Laurence nous a amené comme question, c'est est-ce que l'intelligence artificielle peut être appelée à transformer notre compréhension de l'univers? Et je pense que la réponse est oui, de plusieurs manières, en fait. Un des plus grands mystères de l'univers, c'est que la majorité de sa composition nous est encore inconnue. Donc, comme on a vu dans le diagramme, environ 70% de l'univers est composé d'énergie sombre, tandis qu'environ 25% est composé de matière sombre, et le reste, c'est la matière qu'on connaît. Donc, toutes les étoiles, toutes les galaxies et tout ce qu'on a observé dans l'univers. Donc, c'est encore une très grande question pour les astrophysiciens et les astrophysiciennes. Et l'équipe de Laurence, son équipe de recherche, vraiment tente de répondre à cette question via divers moyens. Donc, d'abord, pourquoi on s'intéresse à la cosmologie? Qu'est-ce que la cosmologie? C'est le début de l'univers. Et ce que Laurence nous a montré, c'est qu'au début de l'univers, c'est très, très complexe et très, très mystérieux. Donc, il y a la partie qu'on appelle la partie de l'inflation, dans laquelle l'univers va s'étendre de manière exponentielle, et cette partie-là, physiquement, est très difficile à comprendre. On a aussi vu que le fond diffus cosmologique est assez homogène. Ça veut dire qu'un peu partout dans l'univers, la température est relativement stable. On a aussi vu qu'il y avait plusieurs problèmes qui étaient causés quand on observait en cosmologie, plusieurs problèmes qui étaient toujours sans réponse, comme par exemple le problème de l'horizon et le problème de la platitude. Et ces deux grandes questions-là peuvent être répondues par les études que Laurence fait dans son groupe de recherche. Et une grande conclusion de tout ça, c'est qu'on ne peut pas observer l'univers tel qu'on le voit aujourd'hui sans comprendre la matière sombre. Ce que je veux dire, c'est qu'on n'aurait pas autant de galaxies, on n'aurait pas autant d'amas de galaxies si la matière sombre n'était pas présente. Et comment Laurence fait pour étudier ce chose-là? Elle va mélanger le big data, donc les données massives, et le machine learning, et elle va s'intéresser, par exemple, aux lentilles gravitationnelles. Qu'est-ce qu'une lentille gravitationnelle? C'est le fait qu'on veut observer un objet très, très loin dans l'univers, mais qui est aligné avec un très gros objet astronomique, comme une très grosse galaxie, qui va déformer la lumière qu'on reçoit à l'observateur, donc au télescope et aux satellites de notre Terre. Et la matière sombre, ça explique comment les galaxies peuvent se coller entre elles. Par contre, comme Laurence nous a dit, il y a énormément de données et ça prend énormément de temps à analyser. Et donc, avec l'apprentissage automatique, on peut accélérer ce processus-là à partir de plusieurs milliers d'années jusqu'à quelques minutes. Donc, c'est vraiment incroyable à quel point l'intelligence artificielle va accélérer notre compréhension de l'univers en accélérant notre analyse des données. Et dans les prochaines années, avec l'arrivée de plusieurs télescopes et de nouvelles, ce qu'on appelle des surveys, ça va accélérer notre processus de compréhension de l'univers, surtout ce qui est dans la matière sombre et ce qui a trait aux lentilles gravitationnelles et au début de l'univers. Donc, on a très hâte de voir tout ça. Et voilà pour la synthèse.